So let's look at the quantum mechanical treatment. Now again, the Hamiltonian basically has the same form. Minus mu dot B for a magnetic dipole in a magnetic field. Well, assuming B is in the Z direction, this will be minus mu Z times B. Now the next B is our applied field, it's just a number. So what are the possible values of mu Z for a quantum mechanical system? Now, let's borrow from let's say a classical treatment. Let's just look at what happens in classically, how we can relate the magnetic dipole moment, let's say of an electron orbiting a nucleus on the average. If you remember, the magnetic dipole moment of a current is just nothing but the current times the area. If you just remember your freshman courses, okay, in your electromagnetic course you have a more general definition of the magnetic dipole moment, but for us this will be sufficient. Well, if there is a charged object, let's say of charge q, with velocity moving with velocity v or speed v, on the average the current that this charge creates around our point is nothing but q over the time, well, the charge passes through every point, through a given point, let's say, once every period. Area is just pi r squared, or this is q over 2 pi r over the speed v times pi r squared, which we can write as, well, the pi's will cancel. This is r will cancel one of them. This is q over 2 times v times r. Or q over 2m times mv times r. But you see, this product, at least in the system, is nothing but the angular momentum of my system. This is L. And also direction-wise, mu is just q over 2m times L for a point object. Well, this relationship also holds quantum mechanically for orbital angular momentum. But for example, if you consider the electron, it doesn't only have the orbital angular momentum, it also has the spin angular momentum. And if you consider the spin, this is the contribution to the magnetic dipole moment of an electron due to its orbital angular momentum. There is a corresponding contribution due to spin. Well, it basically has more or less the same form. But it's not proportional. The factor is not just s, but it's 2s in general. Now, this 2 is called the gyromagnetic ratio. If I'm not wrong, it was first observed experimentally, and then Dirac, when he wrote his equation, he could predict that this should be 2. Then, of course, Dirac equation is just the lowest order term, and in field theory, let's say, you can calculate the corrections to this 2, and it's usually denoted by A. G being the gyromagnetic ratio. So the deviation of 2 you can calculate using quantum electrodynamics, and in fact the calculation for an electron, the first correction or the first contribution to A from quantum electrodynamics was calculated by Schwinger, and he actually got the Nobel Prize for that. And then if you have heard, there was in the recent year there was this muon G-2 puzzle. So basically, we can calculate this A using quantum electrodynamics, using our theories, up to, if I'm not wrong, something like 20 digits after the decimal point. We can also calculate it up to 20-something digits, both theoretically and experimentally. For the electron, there's no problem. But for sometimes, for the muon, there was some discrepancy. There's still some discrepancy between the measured value and the theoretical value, but nevertheless, the discrepancy is quite small. If we can get more precise, more statistics from the experiments and correct the theoretical errors, if they are ready, then probably it will also disappear, but it is still one of the puzzles. Okay, so at least within this course we will stick with the 2. We will take the gyromagnetic ratio to 2. Well, the treatment in your book about this magnetic dipole moment, well, if you have, for the electron, the total magnetic dipole moment of an electron orbiting some nucleus would be given by the charge of the electron, let me put the minus sign also, divided by 2m L plus 2s dot B, or minus E over 2m J plus S dot B. In your book, it says that minus E over 2m G times J. This is not correct. G is not the gyromagnetic ratio. G is what's called Lange's G factor. Gyromagnetic ratio is strictly for the spin. Well, this is not correct. The expressions are still correct, but at least let's do the correct derivation now. The magnetic dipole moment of an electron is not proportional to its angular momentum. It's not in the same direction as its angular momentum because of this factor 2, which kind of complicates the calculation. But let's do it the proper way. Again, we have this our Hamiltonian will be given by minus E over 2m times B times Jz plus twice Sz. Now, of course, remember what we are trying to calculate is Q1, which in this case will be given by sum over all the microstates e to power minus beta ER. ER being the energy of the microstate. You see, if you consider the atom, if you treat the atom, what you usually do is, okay, if you remember the discussion of the hydrogen atom, for example, you start with ignoring the spin, you get the eigenstates, then you add the spin, but when you add the spin, you have to take into account the spin orbit coupling, then you take into account the spin-spin couplings, etc. So the total eigenstates are basically eigenstates of J squared, Jz, L squared, and S squared. So these will be your eigenstates. They will be eigenstates of all these 4 operators. And keep in mind that, okay, it's an eigenstate of Jz, but not Sz. But when we add these terms, so in this basis, in the eigenstates of J squared, Jz, L squared, and S squared, well, the Hamiltonian is no longer diagonal, because you see, Sz does not commute with S. Okay, hold on. Yeah, the same eigenstates will still be the eigenstates, because Jz commutes with Sz, J squared commutes with Sz, right? No. J squared does not commute with Sz. So the eigenstates are not really eigenstates of this additional Hamiltonian when we put it in the magnetic field. But to a first approximation in perturbation theory, we can still treat the eigenstates of these 4 operators as our approximate eigenstates, and the energies will be shifted by this amount, let's say alpha denoting all the other quantum numbers. We have the Jm state minus E over 2 mb Jz plus 2sz alpha Jm. In first order perturbation theory, this is the shift in the energy, which is equal to minus E over 2 mb alpha Jm Jz plus twice sz, no, Jz plus sz, sorry, not 2. It's L plus 2, but J plus S. This is what we need to calculate. Now, then there is the Wigner-Eckardt theorem. Well, what the Wigner-Eckardt theorem tells us is this one. So you have some operators, which we call tensor operators, and K being the rank of the tensor, Q being the component. For example, we will, in our case, we have the Jz, Sz, they are called the vector operators. Their matrix elements are vectors. And then we have the different components of this vector. And just like for an arbitrary tensor, you can define tensor operators. Well, for a given rank tensor, different components are related by rotational symmetry. And Wigner-Eckardt theorem is basically the expression of that relation between the various components of definite states of definite J and M. You see, the dependence on the component only arises from this Clebsch-Gordon coefficient. This is what is called the reduced matrix element. It's just some proportionality constant, let's say, but what is important about that proportionality constant is that it is independent of the M values. Neither of the bra nor of the ket, neither of my tensor operator. All the dependence on M, M prime, and Q are encoded in this Clebsch-Gordon coefficient. Now, in our particular case, yeah, this is basically what we have. So we have some vector operator, not necessarily a tensor operator. We can relate the matrix element of an arbitrary vector operator to the matrix elements of the total angular momentum and the scalar product of the total angular momentum and K. The Clebsch-Gordon coefficients, etc., they are all encoded in these matrix elements. So let me just take this relationship. This is what I will be using. This is the result that we have. Well, let's see, what does that mean? It tells me that the energy shifts, or the energy eigenvalues, up to first order corrections, this is equal to minus E over 2m times B. Well, for that matrix element, I can just write alpha Jm Jz. Remember, this Jz plus Sz is now my K nu. It's the Z component, so I take the Z component of the angular momentum operator divided by h bar squared j plus 1 multiplied with alpha Jm, this matrix element, J dot, well, K is J plus S. Well, I know what this Jz is. So this is equal to minus E over 2m B. Jz acting on this state, you see this state is an eigenvalue of Jz with an eigenvalue h bar m. So there I have h bar m. M is not the magnetization, but the z component of the spin of J, divided by h bar squared j plus 1 times this matrix element. Well, you see, this product I can write in this form. Well, there's the j squared plus j dot s. This is equal to minus e over 2m. Well, h bar cancels one of these, b. M over h bar j plus 1. Well, again, these bras and kits, they are eigenvalues of j squared with an eigenvalue h bar squared j plus 1. Now for j plus s, I can write it as 1 over 2 j minus s squared minus j squared minus s squared. Of course, not plus, it's minus. You see, if we just open up the parentheses over here, this is j squared minus 2js plus s squared. Well, j squared and s squareds are cancelled over here. Minus 2 and this minus 1 over 2 is cancelled. What I remain is plus j dot s. And this will be equal to minus e over 2m b m over h bar j times j plus 1 h squared j plus 1 minus 1 over 2. Well, j minus s is nothing but L. So that is actually L squared operator. And its eigenvalue, well, these kits are eigenkits of L squared, of j squared, and also of s squared. So I can just put in the eigenvalues. H bar squared L plus 1 minus h bar squared j plus 1 minus h bar squared s plus 1. Let me just slightly rearrange the terms. Well, all of them have h bar squared, so I can just take it out. It will cancel one of these h's. So what will remain is minus e h bar over 2m b times m, the z component, divided by j plus 1. Inside, what will remain is, here I have 1 jj plus 1, but here I have 1/2 jj plus 1, so I have 3 over 2 jj plus 1 minus 1 over 2 L plus 1 plus 1 over 2 S plus 1. So this delta E, or in our case nothing but E, because we are just ignoring all the other degrees of freedom. The only degrees of freedom we are assuming is that the electron spin, and in this case also the orbital angular momentum, is given by E h bar over 2m b m 3 over 2 minus L plus 1 minus S plus 1 over twice J plus 1. Now this is the expression for the energy eigenvalues in your book. So this expression is correct, but with the approximations that we are only looking at the first order expansion in a perturbative expansion. And well, there's a minus over here, which I ignored. Well, let's just call that G. You see, for a given system of fixed L and S and J, this is just constant. So the energy shift just becomes minus mu, let me just mu B, G, M, B. Mu B, E h bar over 2m is what is called the Bohr magnitude. Well, then the Q1 for this system. Now the possible microstates for a fixed L and S and J, for us that will be the important one, will be just sum over m of e to power minus beta times mu b g m times b. Now here there is a minus sign. This is sum over m e to the power, let's see, if you remember in the previous case we had the magnetic moment. In this case it will be similar to mu b, the magnitude of the magnetic moment. Then we have the b times the beta as our x. Then here we have g. Let me also include the g over here, because g times mu b is kind of the, in this case at least, it's more or less the magnitude of the magnetic dipole moment. That is what is multiplying b in the energy. And then m. M goes from minus j to j. So Q1, what is that sum?
Where is G over?
Hmm? E to power x m to the power m, where x is mu b g b times beta. What is the first term in the expansion? What is the last term in the expansion?
It's a geometric series, right?
Yeah. How many terms are there?
J, 2j plus 1.
Do you agree?
Why did you do that? I don't know.
Well, okay, how do you sum the geometric series?
If it's a finite number, what are you doing this?
Y to the n. Well, this is y over a plus y to the b, y to the a plus 1. Y to the b. Now, is this wrong? Then you reverse it. No, okay, this is wrong. This is not correct. Now, how do you sum that? This is y to the a times n from 0 to b minus a of y to the n.
I think it's better to take infinity than minus from b to infinity. I think it's better. If you cannot memorize the...
Well, now I do it. This is y to the a, y to the b minus a plus 1. No, okay, sorry, this is wrong. This is completely wrong. This is not geometric series. This is the sum of successive integers. Okay.
Yeah, let's try what I said.
Okay, let's do it your way, which is the correct way. So you are saying that let's do it this way. M from minus j to infinity of e to the power x times m, x to the power m, minus m from j to infinity e to the power x times m. So this is equal to, well, let's take the first term. So this is e to the power minus j times m over 1 minus e to the power minus x. Now 1 minus e to the power x. So when I take this out, it's just 1 plus e to the power x plus e to the power x squared, etc. And that is 1 over 1 minus whatever you are taking the powers. So minus e to the power mj over 1 minus e to the power x. Q1 is equal to minus twice cosine hyperbolic mj. No, sorry, not mj, jx. Cosine hyperbolic xj divided by 1 minus e to the power x.
You have done something like this in the beginning. Did you consider it as an arithmetic series or something?
Yes, yes.
Oh,
Not a geometric series. So that was my mistake. So this is our Q1. Now, first question. When do we expect to recover the classical behavior? You see, one of the important differences between the quantum mechanical behavior and the classical behavior will be the discreteness of the energy levels.
Can show x. X.
Okay, what was x? This is x, and g was equal to
Can you explain what was this result?
Which one? This?
For
You see what we did. We are looking at some electrons. Well, on one hand, we are assuming that they are fixed, so that we are ignoring the kinetic energy. On the other hand, we are not ignoring the angular momentum for the time being. So they have an angular momentum L, spin quantum number S, the total spin quantum number J. And we are saying that, okay, let's fix L and S. Well, S is fixed already, but keeping L fixed is because J is also fixed. So what is the partition function of this system in a magnetic field? Now what we'll be interested, we will be specialized in that case shortly, is let's say we have spin 1/2 particles, they are fixed at different locations. Or you can say that we are looking at atoms actually with a definite J quantum number. Atoms that are fixed in their location, and we are just ignoring all possible internal excitations of the system. And then when we say that, okay, if J is fixed, L is fixed, S is fixed, if only we allow M to change, the Z component of the angular momentum, what is the partition function? Of course, to determine the partition function, first we need to identify the energy eigenvalues. Well, the system is not such a trivial system, but to a first approximation in perturbation theory, we can identify the eigenstates will still be definite states of definite J, M, Jz, and Sz. L squared and S, sorry. J squared, Jz, L squared, and S squared. To a first order in perturbation theory. And now we said that, okay, still sticking to a first order in perturbation theory, this will be the energy shift due to the applied magnetic field. And so since we are just fixing everything else, we can just set the energy of the system to 0 when there's no magnetic field. So the shift in the energy will be the energy of my microstates. So this is the energy. And once I identify the energies of the microstates, my different microstates just are characterized by different values of this capital M, which is the Z component of J, Jz. Then I can write down the partition function. But keep in mind, M, the Z component just changes from minus J to J. So I'm just summing over all possible values of J. So this is my partition function for a single particle. And then, of course, from this, I can calculate the n-particle partition function and the n-particle Helmholtz free energy and the energy, magnetization, etc. Mm-hmm. Or I can just calculate the magnetization from a single particle Helmholtz energy multiplied by n, because basically they are not influencing each other. Now, of course, as in any problem, it's just it will be wise to before delving into the equations or certain limits, etc. What do we expect? Do we have any expectations of the outcomes? For example, one thing is, we already know the classical result. In which limit should this relation go to the classical result?
If you have many particles, then I guess it should go to...
You see, many particles is just a multiplication of single particles. So the single particle should go to the classical result. As I said that one of the main differences between the classical result, classical system, and the quantum mechanical system was the discreteness of the energy. In the quantum mechanical system, the J only take the orientation. You see, what we did in the classical system was we were summing over all orientations. In quantum mechanical systems, not all orientations are possible. Only certain orientations are possible. So if, in a certain limit of the quantum mechanical systems, all orientations would be possible, in that case, we should recover the classical result. Now, you see, for a given value of J, the possible orientations of the angular momentum, let's say this is our sphere of radius J. The Jz can only take either 0, it can be along this line, let's say this corresponds to the case J is equal to 2. So this can be an orientation. This is another possible orientation. This is another possible orientation. This is another orientation. This is another orientation. Of course, just keep in mind that these are, in a sense, not the angular momentum itself, but expectation value, and it is precessing around the z-axis with time. So the angles that J makes with Jz, J makes with the vertical axis are quantized. Not all orientations are possible. In the classical system, all orientations were possible. So in which limit can we say that all orientations of J is possible?
As J goes to infinity.
J goes to infinity. quantum mechanics classical behavior. Well, another thing I would expect is t goes to infinity limit also, we should recover the classical limit. That's what I would expect. Because you see, the discreteness is important because, well, certain transitions will not be allowed when you have the thermalization process. But if temperature goes to infinity, you see, the discreteness will be negligible compared to the thermal energy. So the discrete, the important parameter here will be, you see, if you look at the definition of X, again we have more or less the same thing, mu b, g, b over kt. This is the typical energy, magnetic energy of my system. This is the thermal energy of my system. So if kt is infinitely large, then the discreteness shouldn't be important. That is what I expect. I don't know if it will be verified or not. Now, of course, there are some issues. If j goes to infinity, you see, if you go back to our expression for delta E, you see, this is the quantum mechanical analog. Quantum mechanical energy eigenvalues. Classically, this was minus mu b times cosine theta. Classical energy is always in the range mu b and minus mu b. It's finite. If I just set j to infinity without putting any other restriction on my system, m can take value, infinite value, so it's no longer finite. You see, cosine theta is in fact actually m over j. Well, not strictly, but somewhat, times j. So to recover the classical limit, what we should do is j goes to infinity, but mu b times g times j should be finite. This is what I would, in this limit, and in fact I will identify it with mu in the classical limit. So this is the limit that I will be evaluating. Now, okay, so let me just, rather than going to all the n particle partition function, n particle Helmholtz free energy, let me just look at the one particle. It's because n for n particle, just multiply by n. And x, just to remember, is this one. You see, when we take that limit, j goes to infinity, you see this factor g. When j goes to infinity, this should be finite. G should go to 0. But when g goes to 0, x becomes very small. So basically Q1, the classical limit will be the small x limit. But of course, just pay attention. Here we have x times j. X times j is finite. Because x goes to 0, j goes to infinity. So x times j can still be finite. You see, x times j, x in the quantum mechanical description is mu b times g times j times magnetic field times beta. This is x in the classical theory. When I identify this with mu in the classical theory. So this is equal to minus twice cosine hyperbolic x in the classical theory divided by 1 minus e to power x. But x here is the quantum mechanical x. It is small. So x times j is finite. J is
goes to 0 again.
Sorry?
As j goes to infinity, it goes to 0.
Yeah, x goes to 0. It's very small.
No. X times j goes to 0.
No. Why?
You said g depends on j as 1 over j squared, right?
Well, you see, j, we don't really know what the value of j is, but it takes values between L minus s and L plus s. So when we are looking at the limit j goes to infinity, we are also looking at the limit L goes to infinity. So that ratio is finite.
Okay.
But what is that value? Well, we don't know. I'm just fixing that value, looking at how I will be identifying the classical limit. You see, one thing that I should, if I want to recover the classical limit, the allowed energy values should also be correspond to the classical allowed energy values. I already know that m over j will be the cosine theta in the classical theory. B is already there. So this mu, the magnetic dipole moment in the classical theory, I should identify it with whatever remains, this one. That product I should identify with the magnetic moment, the magnitude of the magnetic moment. Well, it kind of makes sense. You see, we already said that the magnetic dipole moment is this Bohr magneton multiplied with the angular momentum. You see, J is kind of the magnitude of the angular momentum. So mu b times G is some kind of a proportionality factor, times J is actually the classical definition of the magnetic dipole moment. So that's why I identify that with mu. But mu is finite in the classical theory. So the Bohr magneton times this G factor times J should be finite when I take the limit J goes to infinity if I am to recover the classical limit. But that means I should, when I'm taking J to infinity, I should also set G to 0 in such a way that Bohr magneton times G times J should be finite and equal to the classical mu. Only in that limit I might be recovering the classical result. So if that is the case, x times j, you see, x quantum mechanical is this one. Here. This is the quantum mechanical, the x parameter we define in quantum mechanics. In the classical theory, if I if I look at this one, G goes to 0 in the classical limit. B is some external field, beta is some temperature, mu B is just some constant. So G goes to 0. The x parameter I define in the quantum mechanical treatment actually goes to 0. So this over here, this x over here goes to 0. Nevertheless, J, I'm taking the infinite limit of J, but if I multiply the x quantum mechanical and J, what I obtain is just the classical value of classically defined X parameter. Well, I should have probably included this definition of J in the quantum mechanical definition, but let's just keep it that way for the time being. So this Q1 in the classical limit just becomes -2 cosine hyperbolic, let's say X classical, divided by 1 minus 1 plus X quantum mechanical. The ones cancel, so this is twice cosine hyperbolic X classical divided by, well, X quantum mechanical, let's say X classical, times J. This is my Q1 classical. Let's remember what Q1 classical was. If J, okay, there's that J which diverges. But keep in mind that that's just an overall constant, which we can just, when we calculate the partition function, it will not be relevant, or its derivatives, it will not be relevant. Well, there's a mistake probably somewhere. Here we had the cosine hyperbolic, now we have the sine hyperbolic. That is probably, I wrote it wrong over here. Here there's a minus sign. Due to that minus sign, it's not cosine hyperbolic, it's sine hyperbolic. Well, this is also another thing nice when you compare it, your new results with things that you already know. You find your mistakes. So up to overall constants, the classical, in this limit that we defined over here, J goes to 0, J goes to infinity, G goes to 0, such that G times J is finite, we do recover the classical results. You say, okay, there's this overall proportionality constant differences, but as I said, when we are calculating, I don't know, the entropy, the energy, etc., we are basically taking derivatives. And hence these will not be relevant in that case. Any questions?
In the beginning of the class, I saw something like E vector, and you said it's energy, and I didn't get it. It should be in the first page, maybe. Yeah, that's one.
That's what we call a typo. That's
it's
not
E, right?
It's E. No vector.
No vector. So.
Oh, sorry. There's also not E over there. It's the gradient.
It's the gradient. Yeah.
It's the gradient.
Okay.
Yes. Yes. Sorry.
No, it's okay.
It's the gradient of the energy with respect to the components of the B field. If there is only the Z component, then we only obtain the MZ as the derivative of the energy with respect to BZ. Now, tomorrow what we will do is, okay, so we know we have obtained the partition function in the quantum mechanical treatment. We know that the quantum mechanical treatment, at least in a certain limit, goes to the classical expressions, so which is also a justification for our results. And then now tomorrow we can start discussing, we will continue along this line. What is the energy of the system? What is the entropy of the system? Does the Curie law still hold? Well, I would expect it to still hold, because basically it's the temperature, it's the high temperature limit where we should recover the classical results also. And well, okay, hold on. So do we really recover the classical, at high temperatures? Do we recover the classical results? So we only show that when J goes to infinity, we recover the classical results. Okay, fine. But do we recover the classical results at high temperature?
Should we?
I would expect so. If we don't recover, then probably there's something wrong in my interpretation of what is going on, so I should learn something. You see, at high temperatures, what will happen is beta is small, X is small. You see, what we had done over there, we had basically done two things. We said that X is small here, and that this is constant. So as long as this, well, if X is small, I can make an expansion over here. If I make the expansion over here, I recover this one. So I do recover this expression. Exactly the same expression, not with, well, okay, here X just is the X quantum mechanical multiplied by J. So I do recover the classical limit, also in that limit. And then there is the negative temperatures. We should also study what about the entropy of this system. But okay, let's just leave the study of this quantum mechanical system for tomorrow. We already know everything. It's just we will be taking some derivatives, etc. Questions? And then we will start the grand canonical ensemble. Questions? Check your homework for today. Even if you don't write down the solution, just think of how you would solve the problem, so that if you have questions, we can also repeat them tomorrow.